All right, okay. So I will be talking about the talk title called FastSK, Fast Sequence Analysis with Gapped String Kernels. And we provide the link to our GitHub repo that hosting this toolbox we built. It's called FastSK in our QData organization. Please feel free to check it out. All right. So there are two groups of string classification like model families in the literature. The first kind is deep neural network based. They are very, very popular. And the second kind is support vector machine based, SVM based string kernel family. The deep learning DNN based are extremely popular now, but they normally need a lot of training data. So SVM, so in this paper, we actually propose this string kernel based novel string kernel toolbox that needs very smaller training data and to perform very good string classification and with good theoretical guarantees. All right, so what is support vector machine? So support vector machine is just trying to learn to parallel decision boundaries to separate two classes, and so that the distance among the two decision boundaries are as wide as it can. And support when applying using support vector machines, when your X are not completely can be separated in the original space, people create this idea called kernel version, which just map your data samples from the original space not can be separated into a higher dimensional space, which called phi X, and so that in this phi X space you can find like two parallel hyperplanes to separate your two classes. So this is the idea called kernel functions. And the string kernel based SVM formulation is exactly follows the previous page, but figuring out design a family of phi X that map the string input into this high dimensional phi X space so that SVM can separate the two classes well. So this is a page we really want to convince you as SVM, string kernel based SVM still has a very valuable place and to perform string classification. So when we have moderate number of training samples and we compare on one of the transcription factor binding sites prediction task with comparing FastSK versus charCNN and LSTM, both are state-of-the-art deep learning based baselines for this task. And we actually can see, and the DNN-based method just with a huge variance, especially when with smaller number of training samples, and FastSK consistently beat their performance with very low variance. All right, so let's we use 3 case studies to showcase so how our FastSK compared to the state of the art. The first task is predict. It's called transcription factor binding sites prediction, and the input is DNA sequence windows. So in fact, it's just a very simple task. You have a sliding window. You just try to predict, is that sliding window of DNA segments a binding site for a specific TF or not. And in terms of the properties of this type of data, and we can actually tell at each position, there are only 4 kinds of different letters, so which means the dictionary size for this string input is 4. And for some of the TFs, their binding sites, which if you do an equal number of negative, it's smaller. They have really smaller number of binding sites, which makes their training samples are quite small, within the thousands range. So it's a fit for our like the SVM when the SK string kernel is good at. We also tried our FastSK on another task called protein sequence prediction task, and then so this is protein sequence input, right? So the vocabulary size is 20, which is much larger than previous DNA sequence, which is only 4. And then there's certain smaller family protein sequence family they have like positive, and then we want to do equal number negative, which makes the training size it's actually extremely small too, which fits the string kernel can really play a role here. So the third kind of task we actually tried on is a language input task. So the majority of the language tasks now have a lot of training data, but there are certain family still cases they have very smaller training samples. So for example, this medical record based analysis or medical report based analysis, we don't have a lot of trainings labeled instances there. And then in this page, we actually show a different, it's just language prediction. So this is Arabic writers like writing, and you have very limited number just because of we don't cover the set of language don't cover that much. So can you identify a writer's region using just text info? And this also fits the string kernel based very nicely. All right, so let's review the basics of string kernel. So what is string kernel? So the fundamental idea of string kernel is just represent your strings using this bag of k-mer ideas. So I have a sliding window like size k, so k continuous substring. I'm just going to count each substring how many times they appeared in my different sequences, and I'm checking using that co-occurrence, summation of co-occurrence as the similarity of two strings. And because this is a clear exponential sigma to the k space, you need to search on your original and on all of the string you work on. So the search space is actually pretty large. So one of the challenge we try to solve for the state-of-the-art string kernel toolbox is the scalability issue. So they're just too slow. We try to make a much faster tool in this paper. All right, so again, still the basics of string kernels. So there are like different kinds of string kernel family proposed in the literature, and then the most basic one is called the spectrum kernel. The spectrum kernel really just count like what I showed in the previous page. In this one is k equal to 3. You just count how many substrings on all possible 3-mers appeared in the string S and appear in the string T. And then you got this vector representation, occurs representation of S and T. You take inner product. That's your string kernel similarity scores among S and T. So then people don't like this because, you know, in protein, in biological sequences, we want mismatch to be allowed, right? Like insertion deletion. So then people revise that spectrum kernel into something called mismatch kernel. So when I'm computing the two co-occurrence of k-mers, so for example, in this case, when I'm trying to see in the sequence T, its first k-mer is AAA. When I'm counting its co-occurred in the sequence S, I'm not only consider the AAA appearance in S, I'm also considering all those substrings within one mismatch with the AAA. So which in this case, you can have AAC, ACE, and CCA. So because AAA have one occurrence in the sequence T, and you just count all of the possible within one mismatch k-mers in the sequence S, you got that co-occurrence count for the AAA. So then you can actually tell, I mean, this just increased computation dramatically beyond the previous spectrum kernel too, because you need to see this mismatch calculation and search and counting. So these two family of approach all have the issue is the feature space sigma to the k. And the sigma to the k mean just using, let's use protein as example. If you have 20 letter size and then 20 to the k equal to 10, you have 10 to the 13 space to consider. That's your vector space. And this is extremely sparse, and then this also extremely large. And to have all the possible like CAC, all possible k-mers searching in one of the string, it's just certainly not feasible. So people create this idea called gkm-SVM, and then the fundamental idea, it's relatively complicated. I'm not going to talk in details, So in summary, they convert the original sigma to the k space into a new space called gmer based space. And then inside the gmers of each of the strings, and then they search for k-mers. So they created this new idea called the gk-mer idea, and which dramatically actually decreased the search space, that feature space from sigma to the k to something called g times s and t. So please go to the paper to look for details if you are interested more to the details. And this is the equation of the gkm-SVM. I will still also skip the details. And we, in summary, and also the essence of this gkm-SVM is just they convert the kernel calculation into a summation of something called mismatch profiles. And they are using a trie-based data structure to search for mismatch profiles among two sequences at a time. And actually in there is some kind of population based when you have more sequences, how to do it fast. So there are some kind of better designs than what we show in this page. So however, they still have the dependency term sigma to the m plus the s and t, the gmer size related feature is a search related to the trie implementation. So, for example, for one of they're really extremely bad for when you have a little larger than sigma to the 4. So it works on DNA sequences, but it's just almost impossible for the protein or for the language case. So we improved this gkm-SVM by reformulating their formulation into something called a summation of partial kernels. And we also, based on that partial kernel idea, we propose a sorted array-based direct counting algorithm. And also because our formulation is a much simpler formulation, we actually realized you don't need to have all the mismatch profile calculated. You only need the part, and then the calculation converges very fast of the kernel. So I'm going to show you. So this page shows you each one of this is a partial kernel calculation. I will skip the details and because the short talk time. So in essence, we separate the kernel calculation into this P1, P2, and P3. So because we have G equal to 3 and M equal to 1, so that's just without G pick M. So the most important in our case, so you need to perform G pick M partial kernel calculations. So that's in this case is 3 pick 1. And we, for each of the partial kernel, we rely a sorted array-based calculation and to get the partial kernels, and which is much faster than the trie-based implementation. So please refer to our papers for the more details. Because such a simple formulation, then we further propose approximation-based, Monte Carlo approximation-based algorithm. So we actually realize we don't need to calculate all the partial kernels to get the final kernels at all. And in fact, I mean, let's look at this figure. So the red and blue are representing the convergence of AUC and accuracy. And we only need about like 5% of the partial kernels, and our AUC and accuracy already get converges very nicely. And also this orange curve shows you the variance of this kernel matrix after you keep adding the different partial kernels. The variance becomes really negligible after you have the 20%. So this whole figure tries to show you we don't need to do this G pick M all the partial kernels. We only need part. So that's exactly the method we're proposing, and also we implement it. We only just doing a random sample of the partial kernels, and then we observe the variance. When the variance is smaller than a certain predefined values, and we just stop. We don't do the rest, because that's, you can actually guarantee, theoretically guarantee, this is a very good approximation. All right, so let's now compare FastSK. We have that you sample, you have all the G pick M partial kernel calculated versus only in part. So this is the first figure, figure A. In figure A, we can actually show you, and on all of this 26 data sets we had from the 3 different application types, only one data set has using that hyperparameter we tuned, just a slightly like better in the exact method. All of the others, they all converge very nicely to the exact approach. So which means actually we don't need to do, let's just use the approximation version. They're good enough. So the gkm-SVM also have an approximation version, but we actually found out it's behave pretty badly. So look at the C curve, the C in this figure, and when you have a larger G and the gkm-SVM, just the performance drop dramatically when you have a larger G. So we suspect there's some kind of mistakes in their implementation. So we don't recommend people use their approximation version. And the middle figure is to compare. So the x-axis is the kind of computational time, y-axis is the AUC. So the more on this left upper is the higher, like on the left, which means the better, because you are faster and also have higher AUC. So we can actually tell FastSK mostly in this high AUC and low computational region, but the gkm-SVM are all mostly in this low AUC and high computational region. So which we actually, based on that, we conclude FastSK, our fast default version of FastSK is that approximated version. Okay, so now let's compare the speed differences. So this is on the DNA tasks, and we have exactly the same figures for the protein and also the language task. So if we compare the max speed speed up of hours versus the gkm-SVM, on all of the 5 out of the 10, we almost like on average 800% x 800x better in terms of speed. So on the other 4, we are about 100. And if we look at the average speed up, so for that 5, we got about like 100, more than 150x in speed improvement, and the other 5 it's about like 18 better, 18x better. So the protein and DNA case are also in the similar range, about 50x better, yeah, I think, if I remember correctly. So then let's look at the performance. So this is a figure show you x-axis are the baselines. There are multiple different kinds of baseline. They are labeled as different color and different nodes. And y-axis is the FastSK AUC. And then so the diagonal term, if a point is higher than the diagonal term, which means FastSK performs better than the state-of-the-art baselines. So the first figure is for DNA, and there's LSTM, there's char CNN, there's gkm-SVM, there's also GAGO is another baseline string kernel state-of-the-art baseline. And the B is on protein data, and the C is on this NLP text data. So we can actually tell on almost all the data sets in the DNA and the protein case, only in 2 in the DNA case, only in 3 in the protein case. So the FastSK is slightly worse than the baseline, and for all of the rest, more than 20 data sets, we are very dominantly better in terms of the AUC prediction performance. And similarly, in the NLP case, I think there are only 3 cases. The LSTM is slightly better, but all the rest and FastSK is better. So this is a very strong figure showing FastSK predicts well, and then together with the previous page, I mean, it's a very good choice for when you are training data. It's kind of moderate. Okay, so now let's do a little bit sensitivity analysis. So this is FastSK. We show when you varies the G, that's the g-mer size, how the FastSK versus gkm-SVM. So FastSK just scales actually very good with the G. It's almost constant when you have a larger G. But gkm-SVM, I mean, this is actually a log. The y-axis is in the log range. So gkm-SVM, the computation time actually grows exponentially with the G. And then a similar figure for the M when we compare to that mismatch size. So FastSK grows, it's almost like constant with the increase of the M. Again, gkm-SVM grows exponentially with the M. And for a lot of cases, we just cannot, we cannot have those results because it's just so long. It takes too long to get a result. So that's why they stopped earlier. A majority of the gkm-SVM stopped earlier. We also show the gkm-SVM like approximation method, and so their approximation method can't work more than mismatch more than 3. And also we showed in the previous page, and when you have a large G and their performance just drop dramatically. So we really don't recommend I recommend users don't use their approximated versions. All right, to summarize, so we create this tool called the FastSK, which provide very strong string prediction performance, and we show that it just scales with any size of the sequence tasks, like DNA, protein, and language. It also scales really well with this G, which allow this longer substring features to be considered. It also allows more mismatches, and on top of those, we provide a modern software architecture and a usable toolbox through this GitHub repo, and everything made possible by our new conceptually very simple kernel formulation. So that's the end.